Right, the next section on the C3 mind map is allotropes, carbon and nanotechnology. We'll start with allotropes carbon, which are related to examples like graphite and diamond. So we'll have a look at those in particular. But first we have to understand what an allotrope actually is. Allotropes are basically substances that exist as the same element. So in the case of graphite and diamond, they are both carbon. They have the same state. In other words, graphite and diamond are both solids, okay, in this particular example, but they have completely different structures. In other words, their carbon atoms are arranged in a completely different way. So if we have a look at the different structures to start with, in the case of graphite, the carbon atoms are arranged in layers, okay, so literally you have a layer and a second layer and a second layer, and that is the example of graphite, okay. Each carbon atom within that layer is only bonded to another 3 carbon atoms. And each of those carbon atoms are also only bonded to another 3 carbon atoms. So carbon, if you are not sure about this, has the ability to actually form in total 4 different bonds. But in the case of graphite, it only actually uses 3 of these bonds. And what we form is these sheets, these layers, okay, that form the graphite. And in between those layers are weak attractive forces, and we'll come back to those a little bit later. So what holds the carbon atoms together? Well, between carbon atoms you have covalent bonds. Okay, and that's no different in the case of diamond. But graphite forms layers, okay, and that is a really important part of the structure. Again, we'll come back to shortly. In the case of diamond, diamond is completely different. Diamond doesn't form layers. Diamond forms what you would describe as a giant structure, okay, so this is diamond. And carbon has the ability, like I said a couple of seconds ago, to form 4 bonds, and in the case of diamond it uses all of those 4 bonds. So each carbon atom is bonded to another 4. Now this is quite difficult to draw because it's a 3D structure. It's not like graphite where it's a layer. So you have a bond going towards the back attached to a carbon atom, a bond coming to the side, and a bond kind of coming forward. And each carbon is bonded to 4, and that continues to build up to form a very, very, very big structure. So this carbon atom is bonded to another carbon atom, which again will be bonded to another 3 carbon atoms, and it continues to build up. Okay, this structure here is something called a tetrahedral structure, and it's actually a very, very rigid structure. Okay. So it's important to have a bit of an understanding about the structures because it gives you the ability to then start to explain some of the properties, okay? And one thing they have in common, graphite and diamond, yes, they both are the same state, the same element, okay, different structures, is the fact that the thing and the type of bonding that holds the atoms together in both cases is covalent bonding. Okay, so that's quite important to understand, and it helps to explain one key property, okay, of graphite and diamond. So graphite is useful, okay, if we have a look at some of the uses to start with, is useful in many, many ways. Graphite is obviously used in pencil lead. Okay, so when you run your pencil along a page, basically you are losing layers of graphite, okay, on that page. It's also used as a lubricant in things like machinery. So things like pencils, lubricants, okay, are good examples. And both of those use one key property of graphite, and that's this idea of layers. The fact is, in graphite, these layers have the ability to slide past each other. We'll look at why that is the case shortly. And because the layers slide past each other, it basically means that they can be almost slippery, okay, in texture. If you've ever got pencil lead, okay, which is graphite on your fingers, you will notice it feels very, very slippery when you actually rub your fingers together. So that's quite an important property. Now, the reason why those layers have the ability to slide past each other is the fact that in between the layers are very, very, very weak intermolecular forces. And because these intermolecular forces that hold the layers together are so incredibly weak, it means they can slide past each other very, very easily. So that's one kind of key property of graphite, okay? Its ability to be able to be used as a lubricant because of these sliding layers, these weak intermolecular forces that don't hold those layers very tightly. Things like diamond, we obviously see them being used in things like jewellery, for example. And the reason why diamond is used in jewellery is because of the fact that it is lustrous. Okay, it has that fantastic shine, okay, especially when the light catches it. So diamond is quite an interesting material. Diamond is a very, very hard material. And one of the key reasons is related to this structure that we talked about. The fact that every single carbon is covalently bonded to 4 other carbons. So each carbon bonded to 4. Okay, and the hardness of diamond makes it very, very useful. And one key usage that you might potentially see or might come up in exam questions is how it's used in drills. Drill tips, for example, or sometimes you have those massive kind of circular drills, okay, that go through things like rock, for example, will be diamond encrusted. Okay, it'll have lots and lots of diamonds at the tip. And there's 2 kind of key reasons why they use diamond. Partly, it's the hardness, okay, it being such an incredibly hard. And be very, very careful not to use words like strong, okay? That is not the correct word to use. You need to make sure you say that diamond is hard. So the hardness of the diamond makes it a suitable material for drilling. The other thing that makes it suitable for drilling is the fact that it has something again in common with graphite. It has a high melting point. Okay, so different uses for graphite, different uses of diamond are always linked to the properties that they actually have. Okay, so when we start to look at their properties and explaining their properties, this is where some of the key information comes from. Now, in terms of high melting point, this is something that you can use to talk about diamond and graphite. Okay, both of them have a high melting point. Okay, they are both well over 3,000 degrees Celsius. But why do they have a high melting point? Well, it's all to do with the covalent bonds. If you remember, we said that the things that hold the carbon atoms together are basically covalent bonds where electrons are shared. So in the case of diamond and graphite, the high melting point is due to the fact that these covalent bonds are really strong. And the fact is that you don't have 1 or 2 of these covalent bonds to break if you're going to melt that substance. You actually have lots of them. So it's the strength and the fact that you have lots of them that basically means that the amount of energy you are going to need to break those bonds is actually going to be very, very high. So that's one property they share. We obviously have already talked about the fact that diamond, because of each carbon atom being bonded to 4 others, has that strong, rigid structure, okay, that we would call hard. And in the case of graphite, you have those layers that have the ability to slide past each other because of the fact that you have weak intermolecular forces between them. So that kind of changes in terms of the hardness of diamond as compared to the kind of weakness and the slipperiness of graphite. Another property that we need to look at is electricity related to conduction. Now, when we talk about electrical conduction, there is a difference. Diamond does not conduct electricity. Graphite, however, on the other hand, does. Now, electrical conduction is all about either having the ability to have electrons that can move freely, or to have ions, positive or negative ions, that can move freely. In the case diamond and graphite, the key difference is all to do with the electrons that are within the structure. Now, in the case of diamond, each carbon is bonded to 4 other carbons. And that actually means that there are no electrons that can actually move freely within the structure, because they're all involved with bonding. So in the case of diamond, diamond won't conduct because it has no free moving electrons. But in the case of graphite, graphite has got 3 bonding carbons for every carbon. But that means there is an extra electron, and that extra electron has the ability to move freely within the structure. So in the case of graphite, you can explain its ability to conduct electricity by saying it has free moving electrons. So they're the key areas linked to diamond and graphite. Okay, so allotropes, which are the same element, same state, but different structures. The layers held weakly together in the case of graphite, and then the hard, rigid structure of diamond, linking to potential uses. And then the key properties, the high melting point of both of them, linking to the fact that they both have strong covalent bonds and lots of them to break. And in the case of electricity and its ability to conduct, diamond, no, because it has no free moving electrons. Graphite, yes, because it does have free moving electrons. Now, within this section is also about something called nanochemistry. And the word nano is a very, 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 very small, value. So what we're talking about is structures that are so incredibly small but could be incredibly useful. So we're looking at a group of chemicals called fullerenes. And fullerenes kind of break into 2 key structures. The first one is what's called a buckyball. And a buckyball are literally spherical shapes, and they are only made from, in total, 50 carbon atoms. So buckyballs, very, very small, very, very simple structures. You also have nanotubes. And nanotubes are very, very small tubes, again, literally made from a very, very small number of carbons that are literally 1 carbon atom thick. Okay, so we're talking about very, very small structures. There are lots of uses for things like nanotubes in particular, and you need to know some examples of those uses. So one of the first ones are tennis rackets. Graphite tennis rackets are useful because of how lightweight they are. However, if you add nanotubes, so carbon nanotubes, into the structure of graphite, it gives it extra strength. So it's still really lightweight. Graphite is a very lightweight substance, but the nanotubes add to the strength of the structure. Okay, so that's quite useful in particular for people who are playing tennis. Other uses are examples like the fact that nanotubes can also be used as semiconductors. Now, semiconductors are very, very useful when it comes to electrical circuits. And it goes back to what we were talking about related to graphite. They are very, very good due to the fact they can conduct electricity, and it's again linking to that idea of the fact that nanotubes have free moving electrons. Another use would be as a catalyst. Now, they're technically not actually used as a catalyst, but what they are is used as a surface for the catalyst to actually stick to. Now, the good thing about a nanotube is the fact that the surface area is actually very, very large. And that means you can increase how much catalyst you're using. You can increase the surface area of your catalyst, so your chemical reaction, whatever it happens to be, will actually speed up. Another key area is in terms of medicine, and it's something that's being investigated in terms of delivery systems. There are certain medicines, for example, that you don't particularly want to have going directly into the body and affecting all the tissues in your body. So buckyballs, which are these spherical balls of carbon atoms, what they have designed is a delivery system where the medicine can be put into the buckyball, which can then be taken to targeted cells in your body, and then that medicine can be slowly released over time. What this means is that the medicine that could be toxic to other cells will only reach the cells that you actually want it to attack.